to start. So on number 11, as we can see, the two logs have the same base. So that means, like you said, we can just set the insides equal to each other. So b squared plus b is equal to 32 minus 3b. So as we can see, this is going to be quadratic. So since it's going to be quadratic, we want to get everything to the same side of the equal sign. So I'm going to add 3b to both sides. b plus 3b is equal to 4b. And then I'm going to subtract 32 on both sides to get it to my left. That's going to be b squared plus 4b minus 32 is equal to 0. So now we're at the point where we can factor this. So what are some factors of 32 that add up to a positive 4? Negative 32.
8, negative 4.
Good. Positive 8 and negative 4 would work, right? Because they would multiply to give me negative 32, but add up to a positive 4. And then what would be my last step to solve for these? Set them
Equal to 0.
good. Set them equal to 0. So we subtract on this side here. We get b is equal to negative 8. Add. We get b is equal to 4. Now before we can assume that these are both our answers, what do we need to do first?
Plug them back in.
Good. We need to plug them back in to check, because what can't we have inside of a log? A negative or a 0. You can't have a negative or a 0. So if I plug in negative 8 times negative 8 is 64, plus 8, negative 8 or minus 8, that's okay. So this one looks good. And if we plug in 4, we're not going to get a negative either, so both of these answers actually check out. I don't know why it does that. Both of these answers actually check out, so they're both your answer here.
When you plug it back in, do you have to do the log as well?
You don't have to. All you have to check is what's inside the parentheses is not 0 or negative. Any other questions on this? Okay. So number 5 is one of those problems that we want to change the base. So what number do you think I can rewrite these as to some power? Well, 36 I can rewrite as what number to the second power?
6.
Good. I can rewrite this as 6 to the second power. And 6 times 6 times 6 is actually 216. So I can rewrite 216 as 6 to the third power. And now we have common bases. Now, does anybody remember what we do when we put a power to another power? Like this right here?
You add them.
That would be if we're adding them. Yes, we multiply them. That would be if we were multiplying those numbers together. So you multiply here. So remember, this is a common mistake people make, is you have to use the distributive property here. So that's going to be 3x minus 6 equals 6 to the 4x. So everybody just make sure you distribute. Don't do 3x minus 2. You have to distribute that 3 onto both terms. Now once you have a common base, what can you do with the two exponents? You got it. Set them equal to each other. And then from here you're just solving for x. So I can subtract 3x on both sides, which leaves me with negative 6 is equal to x, which means x is equal to negative 6.
How do you know when to use, like, do that when they don't have the same base?
I'm sorry, can you repeat the first part of that?
How do you know when, like, you're supposed to, like, change the base?
Good question. So the reason we know we're going to change the base is if I see something that I know I can rewrite as another number, like it's 36, I always want to try to change the base first, because the log math would be a lot more difficult. So on, like, I believe most of these questions on
Like,
this.
number 2 is like this.
Oh, number 2, okay. I feel like it seems so simple and easy when you do it. I know it always seems like that when you watch somebody else do it. Yeah, we can do number 9. Let's look at number 2 first, though. So number 5, does anybody have any additional questions about it? Alright, so we're gonna move on to 2. So yes, you're asking about 2 because it's not as obvious, right? So I know that 5 to the 3rd power is equal to 125. And if I take 125 and multiply it by 5 again, I would get 625, which means that 625 is the same as 5 to the 4th power to the 3x.
What would happen if you didn't change the base though? Could you still do it?
Yeah, if you want after this, I can show you how you would do it logs. It's long and lengthy, but I can do it. So let's do it this way, and then I'll show you the other way. So then what you would do here is you would multiply these together, distribute, we get 5 to the x, or 3x plus 3, and then what would I do with the exponents? Set them equal. And then you guys can solve that from here. It's just a linear equation. So that's how you would do it if you use the change of base rule. But I can show you how you would do it if you couldn't figure out what to change the base to and you wanted to use logs. So take a second to get this down, and then I'll go to a blank page to do that. Log. So number 2, done another way, you guys are going to have to remind me what it was. It was 625 to the 3x is equal to 125 x plus 1. Thank you. Okay, so what you can do here, if you didn't want to change the base, is you can take the log of both sides. So I would take the log of both sides. And then what can I do with those exponents?
Like multiply.
Yeah, good. So you would multiply them on the outside. So it's going to be 3x times log of 625 is equal to x plus 1 times log of 125. So when you're dealing with log of something, it's really just a number that we don't know yet. So the easiest way we can deal with this is to actually simplify. So this is 3 times x times log of 625. So what I'm going to do in my calculator now is I'm going to do 625 and take the log of that and then multiply that amount by 3. And when you do this, you want to try to save as many decimal places as you can, because that's going to give you the more accurate answer to the problem. So this comes out to be 8.3876x. So I just multiplied this and this together in the calculator. Now over here, I can take log of 125 and multiply it by this. So that's going to be 125 log. That's 2.0969 times x plus 1. So that's what I have so far. So then from here, the easiest thing I can probably do is to distribute this. So that's going to give me 8.3876x equals 2.0969x plus 2.0969. And then I'm going to subtract this over here. So that, like I said, this is the way you would do it if you didn't remember that you could change the base or didn't know what you could change it to. Is equal to, this cancels out this. And then I would just do the math here. 8.3876 minus 2.0969 equals all of this times x. So then I would just divide by that on both sides. So it's not difficult, it's just the numbers kind of get pretty, like, you know, complex. And then x equals, this is approximately 2 divided by 6, which is 1/3, about 1/3, which is what you would have got on the last one. Does that make sense? Yeah, I know it's pretty messy, but that's kind of the other way you have to do it.
I was looking at like 15.
15? Alright, I had somebody...
Someone said something else in there.
Okay.
It's like 9.
They said they meant 19, so let's do 15, and you said 15?
Yeah.
Alright, let's do 15 and 19. Alright, 15 and 19 we'll do. So let me zoom out and get back to where I was. 15. Here it is. Okay. So for number 15, the way you would approach this one is when you have log on one side, you want to get log by itself. So to do that, I would do what with the 5? Good, I would subtract it on both sides. And that's going to give me log base 7 of negative 2b is equal to 2. Once you have that, you're going to use the arrow method. Do you remember the arrow method? Yes. So it's going to be 7 squared is equal to negative 2b, which is 49 is equal to negative 2b. So to find b, I would just divide both sides by negative 2. And b is going to be equal to negative 24.5. Make sense? All right. My other request on here was number 19. Before we move on to 19, does anybody have any questions about 15? All right, so let's do 19 next. Oh, of course, number 19. You always go right for the word problems, huh? All right, so it says here, the graph reflects a 25% annual depreciation of a new boat over 10 years. Derive the decay model represented by the graph. Use the model you derive from part A to calculate the exact value of the boat. And does your calculation match the graph? All right, so basically they want us to use the graph to find a decay model. So this is decay. And this is just regular linear decay. It's not continuously or anything like that. So if we zoom in here, the first thing you're going to want to find is your y-intercept. Okay, this is my y-intercept, and that is at 0, 3,500. So if you remember back to the formula for exponential depreciation, I believe, I don't have any packets anymore, but I believe it's a of t is equal to a of 0 times 1 minus the rate to the t power. Can anyone confirm with me that's the right formula? I have everything right? Exponential decay. It's on 6.5.
Yeah, that's right.
That's right. Okay, I'm just doing it from memory because I don't have my notes. All right, so this right here would be our starting point. This would be our A0, okay? And the rate they gave us in the problem. So the way you would set this up is it would be A of t is equal to your starting amount, which is 3,500, times 1 minus your rate as a decimal, 0.25 to the t power. So that's how you would get the equation. So do I have any questions about how I came up with the equation? Yes?
For the equation, would we keep it as t, or would we plug 10 in since it's over 10 years?
Let's see. Derive the decay model represented in the graph. So no, we're not going to plug in 10 right now because they didn't ask us to find the value at 10. They asked us to derive the model represented by the graph. So if I were to plug this into like decimals right here, this would model this graph.
Okay.
So just because of the way the question was asked, they weren't asking about a certain specific time, they were asking about the equation in general. Does that make sense?
Yeah.
Okay. Anybody have any questions about how I knew to use this formula, anything like that? You guys feel good about that then? Okay. And then why you need to use the initial point, your y-intercept. Okay. So then it says, use the model you derive from part A to calculate the exact value of the boat after 6.5 years. So all you're going to do here is you're just going to take your formula and you're going to plug in 6.5. Now, how did I know I didn't need to convert my 6.5 to another unit? Anyone know? Bless you. Bless you.
Because it's a new.
Yeah, it's in years. Good, and see how the graph is also in years, and this everything's in years, so it's okay to go. So then we would just do that math, and we would get 1 minus 0.25, so 0.75, to the 6.5 power times 3,500, and that comes out to be $539.47. So the boat's value is only that much after 6.5 years. And does your calculation in part B match the graph? So to figure that out, we would look at our graph at 6.5 years and see if it matches. So 6.5 years would be right here. So what do you think? Does it match what we came up with? Yes, it does.